Now, let's generalize our calculation of the average number of solutions of a random SAT formula to the case of k-SAT, having k variables per clause instead of just 3. Because it's interesting to think about how the threshold scales with k. So if we generalize our argument from before, well, remember that a random 3-SAT formula is satisfied by a particular solution with probability 7/8, because it has to disagree with it in all 3 places to be unsatisfied. You know, these OR clauses are pretty easygoing. There are k ways to satisfy them. In the same way, a random k-SAT clause with k variables is satisfied with probability 1 minus 2 to the minus k, because it only disagrees in all k places with probability 2 to the minus k. If we follow the same argument as before, this predicts a value for the threshold which grows exponentially with k. Indeed, it grows as 2 to the k times the natural log of 2. All right. But remember, this is only an upper bound, not a lower bound. So it was an open question for a long time whether this is close to the truth or whether it's a huge overestimate. It turns out that this is pretty close to the true threshold, which is just a constant below this as k gets large. So this is a decent estimate of where these random SAT formulas cease to become satisfiable. And up to this threshold, there are almost always solutions. But can we find them? Algorithmically speaking, can we actually find these solutions, for instance, in polynomial time? Or is there some point at which it gets hard? If you remember from earlier, we had this graph of the amount of search time that a backtracking search algorithm needs. And there was this zone below the threshold where it seemed to get hard to find solutions. So can we analyze this zone rigorously? And can we find that indeed there is a range of densities where solutions exist but are hard to find? Well, let's analyze a simple search algorithm. And it's going to be kind of the stupidest search algorithm you can possibly imagine. Let's first describe what happens to a SAT formula as you start to try to solve it by setting some variable. Well, every time you set a variable, if a clause has that variable in it, if that variable takes the value, if you give that variable the value the clause wanted, well, the clause is happy. It goes away, because after all, it was the OR of these 3 things, or k things, and you just made it happy by giving it one of the things it wanted. It essentially disappears from the formula. On the other hand, if you set this variable with the opposite value from what the clause wanted, it says, well, there's still 2 ways to satisfy me. So for instance, the clause x or y or z, if it wants to be at least one of those to be true, if I set x false, it turns into a 2-SAT clause that wants y or z to be true. If I then set y false, well, now there's only one way left to satisfy this clause, namely setting z true. If I now set z false, there are no ways to satisfy this clause. It just sits around being depressed. It has 0 variables. There's no way that it will ever be happy. Well, this is the same as saying we've hit a contradiction. In terms of our backtracking search tree, this would be a dead, lifeless branch, and we would have to go back to a previous branching point and try setting some variable in a different way. Okay, but let's analyze an algorithm which doesn't backtrack at all. It just charges ahead. It sets variables permanently. And if it reaches a contradiction where some clause has just become empty, it says, oh well, sorry, I failed. Maybe next time if I follow a different random branch. Okay, this is the kind of algorithm which we're going to analyze. Well, it's not very smart, but maybe it will work some of the time as long as the density is low enough. We're going to make one concession to intelligence. This algorithm will do one smart thing. Whenever there is what we call a unit clause, a clause with just one variable left in it, where all it wants, the only way to make it happy is for this variable to be true or for this particular variable to be false, we'll give it what it wants. So if there is a unit clause, we will set its variable the way that it wants. This might get us in trouble with some other unit clause. That's life. Okay, that's what we'll do. On the other hand, if in our current picture of the problem, with the remaining clauses that have, after we've satisfied some and shortened others, if there is currently no unit clause, if all the clauses have two or more variables, we will pick randomly from all the variables that we haven't set yet. We will flip a coin and set it true or false with equal probability. So if there aren't any really urgent unit clauses demanding that particular variables take particular values, we'll just give a random variable a random value. And that's our algorithm.